Hello, welcome to Taxonomy Online Mathematics. In this episode, we want to have a tutorial lesson on small change as a continuation of the application of what? Differentiation, calculus 3. So in this episode, we are taking the introduction into how to find small change of any quantities given unto us. So one, we have to consider two variables x and y. Those are the variables we want to consider. So if the x increases by a small change, that is the delta x, by using dx. So this is the delta x. Then y also increases by a corresponding small amount, delta y. So if there are two variables, if x is increasing, the y is increasing, correspondingly almost the same amount. So where x is sufficiently small within 1% of the exact value, we can have the ratio of the delta y over delta x to be approximately equals to the dy dx, the differentiation of the y with respect to x. All right. So as the small change of x, as the delta x is approaching 0, we can say that delta y over delta x will be tends to, or will also approach to dy dx. So that simply means if I want to find the small change in y, that will be approximately equals to dy dx times the small change in x. That's the dx. All right. So this is the approach. Remember, as we are making delta y to be the subject here, then delta x multiplying. We can as well make delta x the subject, whereby delta a will multiply. You only reciprocate the dy dx. Okay, so this concept should be one key term that we'll be using, agreeing that as the change of x is within sufficient 1% and delta x is approaching 0, this is going to be the final conclusion we are going to have. So if I have a question like this, the side of a square is 5 centimeter. Find the increase in the area of the square when the side expand 0.01 centimeter. We can see the difference between this and a rate of change is that there is nothing here called rate. And even this should have been centimeter per second if we are dealing with rate of change. So this is just a small change. So from here, so what are we going to pick? In this environment, we can just say let L be the length, right? So if L is the length of the square, then we can say L is equals to 5 centimeter. What we have been given. They said the length, the side of the square is given as L. So if it is L, that will be 5. Then delta L. Delta L, which is the small change. The small change in the L will be given as 0.01. So that is what we have. So now we have this. What is next? The parameter mentioned is area. So we can also say the area of, let me just use A. The area of a square is given by L what? Square. So if that is the case, we have L square, we have L. What are we looking for? We need to find dy dx. So that means I can find the A, the L to be equals to 2 come forward, 2L. Do we get that? We are going to make use of dy dx. So for the small change, we can agree that the small change in the area divided by the small change in the length should be approximated to the A, the L. So now we are looking for the change. So therefore, the small change in A, that is the area, will be equals to dy dx times the small change in what? The length. So you can see we have made use of the same section where we are looking for the small change in the dependent variable equals to the dy dx times what? We can use this as approximation. Then we substitute the values and see what that will give us. So from here, I can say delta A is approximately dy dx. Where is the dy dx? Okay, it should be the L, right? The L. And that will be giving us 2L in this case, multiplied by the small change in L, which is 0.01. But we also know that the L is given to us as 5 centimeter. So our small change in area become 2 times 5 times 0.01. So 10. That will be 10 times 1 over 100, right? So this cancel 1 over 10. That will be 0.1. So therefore, we can say therefore the increase in area is going to be 0.1 centimeter square. Are we doing centimeter? Yes, centimeter square. So that's one way by which we can get it, following the tutorial we have in the beginning, the explanation we have in the beginning. But we can also use a second method to arrive at which I have not discussed. So we can say method 2, or alternatively, if we are having A equals to the L square, we are saying there is a change in what? A, small change. That will mean the A plus that small change will be equals to the L, which is L plus that small change. The L plus the small change. And we are having a square of that. The L, the change in L, the small change in L square. We are having the L square. So now we can expand this to have A plus the small change equals to, you square the first twice their product. So 2L delta L plus delta L square. The delta is part of the square, so let's take it out. So now what do we know about the A? The A is L square. So I can have L square plus delta A equals to L square 2L delta L plus delta L what? Square. So now we can see that if we group like terms, the L square and the L square will cancel, leaving delta A equals to these two sides, right? So from here, you'll be having delta A, the small change, equals to 2L delta L plus delta L square. So you're only going to do substitution, right? So 2 times L, 5. Delta L, 0.01 plus 0.01 all squared. You know already this will be giving you 0.1 plus 0.001. All of them together will also give you 0.1. That's 0.1001, which in the same one decimal place will give you the same. So our area will just be centimeter square. So even though we have dealt with the formula, we can still also take it in this aspect to find the small change if we are asked to find without remembering the formula. I guess you can look through and weigh the two formulas and pick the one that resonates with you. Thanks for watching. Like, share, comment, and subscribe.